Hello everyone, this is Bingyu again. By now you should have started the second module of CE 170 on traffic modeling, and I hope that you are finding it interesting so far. In the quiz and exercise of this module, you will be asked to run some simple traffic simulations. We'll provide you with all the inputs, but I feel it might be helpful for you to understand how we generated them. So this notebook is a demonstration of all the steps that we have taken to generate the inputs. Now, click on this button to open the notebook. Click Copy to your drive. Okay, now we are here. The notebook is divided into 3 sections. The first one is about how to retrieve road network data. And the second one is about how to build the traffic travel demand. And the last one is to do simple shortest path calculations. This covers the supply, demand, and the behavior side of a simple traffic model. Okay, let's get started on the first section. So talking about road network data, the OpenStreetMap is a really good source of it. So I'm going to introduce 3 methods to retrieve road network data from the OSM. And depending on the size of your problem, you may choose either one of them. Okay, so for small jobs that you want to really quickly get the data, you can use this website called Overpass Turbo. So when you go to this website, it looks like this. This is the Berkeley campus. And let's first type out some information on the left box. So we want our output data to be in JSON format. We are only interested in the road links. And we only want residential rows. Let's bound our selection in the bounding box. Okay, after we finish typing this, we can use this button to manually select a bounding box of the area that we are interested in. Suppose we just want to know some information about this one street. Well, usually you want to know the data on more streets, because one street you can easily find that information directly on Overpass website. So let's run the query. Okay, so there seems to be an error. Let's repair it. Is this the problem? Okay, so now it gives me this information saying that the query returns no nodes. But anyway, let's just see the data first. Okay, so this is our query. So Overpass Turbo is able to give us the information of the road, including the OSM ID, the nodes that form it, the type, speed limit, and some other things. But as the prompt box said before, it doesn't have the information of these nodes, which we really need if we want to, for example, make a map of this road. So let's repair our query to also get the nodes of this link. Let's see. Okay, so now we have not only the way element, but also the information of all the nodes that form it, including their coordinates. You can copy paste this data to your own text editor and then further process on it. And sometimes if you want to download the information for a large area, sometimes the downloading process could take half an hour or even more than 1 hour. It's better to use a script. For that, we can use Overpass API. First, we create a query file. So the query file is super long. It looks complicated, but actually the structure of it is really simple. So let's look at it. So still we want the output to be in JSON format. And then we apply a filter to the type of the link elements. So we want motorways, trunk road, primary roads, up to or down to residential roads. So this system is the British road category system that like OSM uses. So maybe you're unfamiliar with it, but motorway is the most important ones, and followed by trunk roads, and then primary, secondary, tertiary, and then the residential roads. Next, we need to give a bounding box, so a polygon bounding box of the area that we want to run our data collection on, and get all the nodes for these way elements as well, and save it to a query.osm file. So let's run this query, run this command. When it finishes, okay, we can go to this file directory and you can see this query.osm has been created. You can download this file and it will look exactly the same as the red text here. And then based on this query file, we can query for the road network data from this Overpass API website. And the format is still wget, and we want the output to be called target, and then our query file and this API address. Okay, so let's refresh the page and we will see this target.osm being created. You can download this file. It will be a bit larger, but the format will look exactly the same as here. Okay, so the above two are good methods to obtain raw data from the OpenStreetMap. But actually the raw OpenStreetMap data is not sometimes it's not clean enough. It will have some errors, and it may have some redundancy in it that we don't really want to deal with. And in fact, these days, my go-for method to retrieve raw network data is to use a Python package called Osmx. This package was developed by Jeff Boyne while he was a PhD student at UC Berkeley, and I have to say that it is a really really good Python package. And so the official document recommends to install it with Conda, but because Conda is not supported on Colab, so we'll just use a traditional pip installation method. After installing this OSMNX extension, we can download this North Berkeley boundary map, so that will define the boundary of our query. Okay, it may take some time, but not very long. Okay, now it's finished. Let's try to see if it is working properly. Okay, seems everything is fine. Let's just clear the outputs first. Okay, we are here. And then in OSMNX, it's really handy that you can just give it an address that you want to get the road network data around. So for example, this is the address around the north gate of the Berkeley campus. We can just download the data using this one line and then plot the network. Okay, so now it's finished. So we give our center point around here, and it automatically downloads and cleans the data for the network around it. If we want to have more control, we can define the shape of the bounding box, of the boundary of our query. For example, that's the one that we have just downloaded. So this defines the North Berkeley boundary. And we can get the geometry of it and give this geometry as input to the OSMNX function, and then download the network. So this will take slightly longer. Okay, so this is the road network of North Berkeley, and the Berkeley campus is here. And this is how I created the original data for your quiz 3 and assignment 2. But I did some further processing, so it doesn't look exactly the same. We can then convert this graph to geodata frames, and it will have lots of information. This may look familiar because this is the data that we use for our Python exercise 5. And for Osmx, you can easily download data for a whole city and sometimes a region like the Bay Area, although that may take some time, so you just leave it to run. Let's see the road network data that we have downloaded in QGIS. Okay, so this is the road network data that I have downloaded for your assignment and also the quiz. So I modified it by and removed some of the very short rows, very short road links. And also I created this virtual sync node to denote a safe destination if we are going to, for example, simulate the evacuation of the Berkeley Hills area. Okay, so that's pretty much the methods to download the road network data. And then the second part, the second section, we are going to talk about how to create this travel demand. And to be honest, creating travel demand is the most challenging task in building a successful traffic simulation, because usually we won't have such data. Like some potential sources of travel demand data include the regional travel surveys, or increasingly, there are companies that provide this like travel demand data based on the mobile phone signals. But as you can imagine, these data are not a lot, and sometimes they are like not very like accurate or doesn't have good spatial resolution. So there is also another way to create them based on some models based on the land use type of the area. So if it's residential, then there will be more trips coming out of that area in the morning. And if it is more like business districts, then it may have more trips like leaving that area in the evening. And we're not going too deep into that area, so we'll just use a simple case. For example, we want to create a travel demand file of people evacuating from the Berkeley Hills area to a safe destination. So this is the example of the travel demand file that we want to achieve. So it has several columns, including the trip ID and the start node location, end node location, and then the departure time. And for our assignments, we're going to simulate evacuation. So we will first create an evacuation zone. We can do that in QGIS. So for example, we want to create a new shapefile layer, file name. So we need to test evacuation and change it to polygon. Hopefully it will be good this time. Okay, so now we have this empty shapefile layer. We want to edit it, create a new geometry. For example, this is the area that we think it is dangerous and people should evacuate, and give it an ID. Okay, so now you can save the changes and stop editing it, and then export it, save the feature, as a CSV or shapefile or whatever you prefer. So previously I have created this evacuation zone, and it looks like this. And this is the evacuation zone that we'll use for our assignment. And that is what it looks like with the road network. So basically, all people living in this purple area needs to evacuate, and their evacuation origin will be one of the nodes. Okay, so we can get that data, the evacuation zone data on the collab using this wget that I have put the evacuation zone. Okay, so I have uploaded the evacuation zone on our GitHub repo, and we can get it using this wget command, and then we can import some necessary Python libraries. Okay, let's see if it's downloaded. Okay, so our evacuation zone is downloaded. Next, we want to find which nodes are inside that evacuation zone, and the nodes inside the evacuation zone will become the origins of the trips. So we can first load all the nodes and convert it into a geospatial geodata frame. And then we can do the same for the evacuation zone. So now we have two geometry data frames or geometry files. One is the node locations and the other is the evacuation zones. Then we can find out which zones are inside this evacuation. Then we can find out which nodes are inside this evacuation zone by using a simple intersect command. And if your data is a bit complex, for example, if you have a really complex evacuation zone, or if you, for example, if you have a complex evacuation zone, or if your the bounding box of your point layer is much larger than the evacuation zone, you can take advantage of the spatial index and get a faster query. And after this step, we can create this OD data frame where the origin nodes will be the nodes inside the evacuation zone, and the destination nodes will be the virtual sync points, the virtual destinations that we think is the safe destination. So let's run it. And this will be our OD file. So the origins are nodes inside the evacuation zone, and the destinations is a virtual destination that is linked to the network. So once people have reached certain parts of the network, they'll be considered safe and directed to this virtual sync node. Okay, the last part of today's demonstration is on shortest path calculation. The shortest path calculation has a really special place in traffic simulations because it is a basic assumption that people will take the shortest path to get to their destinations. In more complex simulations, this assumption will be more realistic. For example, people are not only following the shortest path, they are sometimes following the fastest path, the safest path, or most familiar path, or even a combination of those factors. But all those can be based on the shortest path calculation. There are many packages in Python that can do that, including NetworkX, Python iGraph, but we are using one that is specifically developed for our case, which is called SP. So the SP is a C++ code that has a Python wrapper. Usually you have to compile it on the platform that you are using. But here we want to save time, so we just provide a compiled dynamic library compiled on the collab. So let's get it, and also our Python wrapper, and then the road network data that we'll be using. And then install some, import some necessary Python packages. Okay, now it is finished. And we can see this SP is here. So first we have to read in the road network edges file into this data frame and see the first few lines of it. So this is the road links file that we'll be using to create the graph. And then the shortest path queries are run on a graph. So we need to create this graph object directly from this data frame, give the start node ID, end node ID, and then the weight column. So here we choose this free flow travel time as the weight of our graph. So the shortest path will become the fastest path. And let's run this again. Okay, now it's finished. And let's try to get a path from this CE department from the North Gate to a popular restaurant called Cheeseboard Pizza in Berkeley. And we can find out the OSM IDs on the OpenStreetMap. And then we can also find the graph node IDs in our QGIS. So for example, we want to find the graph node ID of this CE department starting location. So the CE department is here and the North Gate is here. So let's assume the starting location is this node 191 and Cheeseboard Pizza is around here. Yeah, it's around here. So we'll set 170 as our destination. Okay, so this function will help us to get the path on a graph from the origin node to the destination node. So we can query for the path and calculate the distance. Sometimes if the path cannot be found, it will return a really large distance. And if this is the case, then we say this path has not been found. Otherwise, you will get all the nodes along this path, and we will return this route object. So let's specify the origin is 191, the North Gate, and destination is 170, somewhere close to the Cheeseboard Pizza. And then we can calculate the path by calling this getPath function and get the travel time. So the travel time is only 3 minutes. It may be too fast, but considering that our assumption is that people are traveling at the free flow speed, so that would be like if you start from the north side of Berkeley and want to go to Cheeseboard Pizza in the midnight, and there's no other cars on the road, and you are driving at the maximum allowed speed, and this will be the travel time. The next one, we can visualize the result using this block of code. Specifically, we are using a Python visualization library called Volume. And this is the path that SP Code has found. It's pretty realistic. Okay. And so in our quiz 3, we will run this shortest path calculation for multiple origins and destinations and count how many vehicles or how many trips have used each road. That will be a static traffic assignment. And then in assignment 2, we will run a more dynamic case. So in that case, we'll first calculate the path of each individual vehicles, and then we will gradually move the vehicles along the road. And by that, we can create more realistic congestion outcomes. Okay, so that's all I want to say about how I prepared the input data for your quiz and assignment, and hope you will continue to enjoy this module. Thank you.